Next, let me review one-to-one and onto function. Let f be a function from A to B. Here A is called a domain, B is called a codomain. We say f is one-to-one if for all S1, S2 in the domain, f of S1 equal to f of S2 implies S1 to S2, which means for every output, there exists a unique corresponding input. For every output, there exists a unique corresponding input. Next, we say f is onto if for every y in the codomain, there exists x in the domain, such that f of x is equal to y. If f of x is equal to y, that means y belongs to a range. If f of x equal to y, that means y belongs to a range. So, for onto function, we can say it in a different way. Or in other words, we say f is onto if its range is the same as its codomain. Only other words, we say f is onto if its range is the same as its codomain. Next, let me show you some examples about one-to-one and onto functions. For example, let f from real number to real number be defined as f of x equal to 2 to the power of x. Then its graph looks like this. Its graph looks like this. We can see that this function is one-to-one because for every output, there exists unique input. This function is one-to-one because for every output, there exists a unique input. But this function is not onto. This function is not onto. Negative 1 belongs to the codomain. Negative 1 is a real number belongs to the codomain. But 2 to any power won't be negative 1. 2 raised to any power won't be negative 1. So negative 1 doesn't belong to a range. Since negative 1 belongs to the codomain, it doesn't belong to a range. This function is not onto. So here f is one-to-one, but not onto. Because negative 1 belongs to the codomain, but it doesn't belong to a range. So this function f is one-to-one, but it's not onto. Another example. Let g be the function from real number to real number be defined as. Let function g from real number to real number be defined as g of x equal to s cubed minus x. Its graph looks like this. Its graph looks like this. Here, in this function, g of negative 1 is 0, g of 0 is 0, and g of 1 is also 0. If two different inputs give the same output, this function is not one-to-one. But this function is onto. But this function is onto because for all y in the codomain, we can always find corresponding x in the domain, such that f of x equal to y. So g is onto. That's an example. F is one-to-one, but not onto. G is not one-to-one, but G is onto. Next, let's create a theorem. Let A be an m by n matrix, and let T sub A from Rn to Rm be the matrix transformation associated to A. If the rank of A is m, then T sub A is on 2. Here we try to prove that T sub A is on 2. In order to prove T sub A is on 2, we can try to prove that the range of T sub A is in a sense a codomain of T sub A. We try to prove its range is in a sense its codomain. Let's prove it. Since the codomain of T sub A is Rm, that's the domain, that's the codomain. Then the range of T sub A is a subset of Rm. Because for any function, the range is always a subset of the codomain. So the range of T sub A is a subset of Rm. Next, since the range of A is M, and we know that the rank of A is in a sense the dimension of the column space of matrix A. Then the dimension of the column space of matrix A is also M. And according to earlier theorem, we know that the column space of A is always in a sense the range of T sub A. The column space of A is always in a sense the range of T sub A. Hence, the dimension of the range of T sub A is M. Because the column space of A is always in a sense the range of T sub A. So their dimension must be the same. Next, since the range of T sub A is a subspace of Rm, range of T sub A is a column space, it's a sense a column space, which is a vector space, and it's a subset of Rm. That's why it's a subset of Rm. Since range of T sub A itself is a vector space, and it's a subset of Rm, that's why it's a subset of Rm. And the dimension of the range of T sub A equal to M, which is in a sense the dimension of Rm. If a subspace of Rm has the same dimension as Rm, they must be the same. If a subspace of Rm has the same dimension as Rm, they must be the same. If a subspace has the same dimension as a vector space itself, they must be the same vector space. They must be exactly the same. Then the range of T sub A must be the same as Rm. Since range of T sub A is a subset of Rm, it has the same dimension as Rm, so they must be the same. If the range is the same as the codomain, so the range of T sub A is in a sense the codomain of T sub A. Since Rm is a codomain, of T sub A. Since the range of T sub A is in a sense the codomain of T sub A, then T sub A must be on 2. If the range is in a sense the codomain, T sub A must be on 2. That completes the proof of this theorem. Note, in the above theorem, M must always be less or equal to N. If M is greater than N, then T sub A can never be onto. If M is greater than N, we know that the dimension of the range of T sub A is the same as the dimension of the current space of matrix A. And the column space of matrix A is the span of all column vectors in matrix A. It's the dimension of the span of all column vectors. C1, C2. How many column vectors do we have here? Here A has m rows and n columns, so there are n column vectors. We have C1, C2 up to Cn. In a span of n vectors, its dimension must be less or equal to n. And we know that n is less than m. So the dimension of range of T sub A is strictly less than m, which means dimension of range of T sub A is not m. Since the dimension of the range of the codomain is Rm, and the dimension of the range is not m, then they cannot be the same. Since all bases in the same vector space, all bases must have the same number of vectors. If two vector space has different dimensions, they are not the same, they cannot be the same. If they are the same, all bases must have the same number of vectors, that means their dimension must be the same. Since their dimensions are not the same, they cannot be the same vector space. Then the range of T sub A is not the same as the codomain of T sub A. Hence, T sub A cannot be onto. So in the above theorem, M is always less or equal to N. Otherwise, T sub A cannot be onto. Next theorem, let A be an n by n matrix, and let T sub A from Rn to Rm be the matrix transformation associated to A. Then T sub A is 1 to 1 if and only if the kernel of T sub A is 0. Here, this statement is in the form of if and only if. When we prove it, we must prove in both directions. We first assume T sub A is 1 to 1, then prove kernel of T sub A is 0. Next, we assume the kernel of T sub A is 0, and prove that T sub A is 1 to 1. Let's prove it in both directions. First of all, from left to right. So, assume T sub A is 1 to 1. We try to prove that the kernel of T sub A is 0. So I first of all let X belong to the kernel of T sub A. Then T sub A of X is 0. Because kernel is the set of all X such that T sub A of X is 0. Since X belongs to the kernel, then T sub A of X is 0. Also, we know that any matrix transformation is a linear transformation. So T sub A of 0 must be 0. Since any matrix transformation is a linear transformation, So t sub a of 0 must be 0. So we have t sub a of x equal to t sub a of 0. Since they both equal to 0, t sub a of x equal to t sub a of 0. Since t sub a is 1 to 1, since t sub a is 1 to 1, then what's in the parentheses must be the same. Then s equal to 0. For any 1 to 1 function, if f of s1 equal to f of s2, what's inside the parentheses must be the same. Here, since t sub a is 1 to 1, then what's in the parentheses must be the same. So s equal to 0. Since the only vector in the kernel is 0, we say kernel of t sub a is 0. Since every vector in the kernel is 0, the only vector in the kernel is 0. So kernel of t sub a is 0. Since all x in the kernel is 0, that means the kernel of t sub a is 0. Let's complete the proof from left to right. Next, let's prove from right to left. Assume the kernel of t sub a is 0. We try to prove that t sub a is 1 to 1. So, in order to prove a function is 1 to 1, we try to prove that f of s1 equal to f of s2 implies s1 equal to s2. So, let s1, s2 be two vectors in the domain. Assume t sub a of s1 equal to t sub a of s2. Then this equation can be rewritten as t sub a of s1 minus t sub a of s2 equal to 0. Since any matrix transformation is a linear transformation, this expression can be written as t sub a of s1 minus s2 equal to 0. Since any matrix transformation is a linear transformation, so t sub a of s1 minus t sub a of s2 can be written as t sub a of s1 minus s2. Then, since the kernel of t sub a is 0, the only vector can make t sub a equal to 0 is the 0 vector. Since kernel of t sub a is 0, the only vector can make t sub a to be 0 is the 0 vector. Then s1 minus s2 must be 0. The only possible vector here is 0, is a 0 vector. Since s1 minus s2 is 0, then s1 must be the same as s2. Let's prove that t sub a is 1 to 1 because t sub a of s1 equal to t sub a of s2 implies that s1 equal to s2. So t sub a is 1 to 1. Let's complete the proof. So t sub a is 1 to 1 if and only if the kernel of t sub a is 0. Next, let's go back to the equivalent statements. Let A be an n by n matrix. Then the following statements are equivalent. In the earlier sections, we know that the first 7 statements are equivalent, which means if one of the statements is true, then all statements are true. If one of the statements is false, then all statements are false. Today, I'll add more statements to the equivalent statements. I'll add 6 more statements here. Statement A says the column vector of A are linearly independent. Statement 9 says the row vector of A are linearly independent. Statement 10 says the column vector of A spans Rn. Statement 11 says the row vector of n spans Rn. Statement 12 says the column vector of A form a basis of Rn. Statement 13 says the row vector of A form a basis of Rn. We try to prove that all these statements are equivalent. since all 7 statements are equivalent, since the first 7 statements are equivalent, if I can prove that all these 6 statements are equivalent to statement 7, then they are all equivalent. So let's try to prove that all these 6 statements are equivalent to statement 7. I'll prove like this. I first of all prove that statement 7 implies statement A. Statement A implies statement 10. Statement 10 implies statement 12. Statement 12 implies statement 13. Statement 13 implies statement 11. Statement 11 implies statement 9. And statement 9 implies statement 7. Let's prove it. Let's first of all prove statement 7 implies statement A. Seven implies A. Statement 7 says determinant of A is not 0. So we assume determinant of A is not 0. We try to prove that the column vectors of A are linearly independent. So assume determinant of A is not 0. We try to prove that the column vectors of A are linearly independent. Let C1, C2, Cn be the column vectors of A. We try to prove that C1, C2, Cn, they are linearly independent. So I set K1, C1 plus K2, C2 plus Kn, Cn equal to 0. If the only solution for this vector equation is K1 equal to 0, K2 equal to 0, and Kn equal to 0, that means C1, C2, Cn, they are linearly independent. And for this vector equation, its augmentation matrix can be written as the augmentation matrix of the above vector equation can be written as the matrix with component of C1 in the first column, component of C2 in the second column, and so on, component of Cn in the nth column, then followed by component of 0. Component of 0 vector is 0, 0, 0, 0, 0. Then this is matrix A, C1, C2, Cn. Together, this is matrix A. So the above augmented matrix can be written as as AX equal to 0, where X is the vector of components K1, K2, Kn. X is the column vector K1, K2, Kn. this is a homogeneous system of linear equations. If the determinant of A is not zero, the homogeneous linear system of equations has only trivial solutions. Since determinant of A is not zero, the homogeneous linear system of equations AS equal to 0 has only the trivial solution. Which means x must be 0. Only trivial solution means the only solution is s equal to 0. If s is 0, that means k1 is 0, k2 is 0, kn is 0. Means k1 is 0, k2 is 0, and kn is 0. If all k's are 0, if all k1, k2, kn, if they are all zeros, that means c1, c2, cn, they are linearly independent. Hence, the column vectors c1, c2, cn, they are linearly independent. Let's prove that 7 implies A. If determinant of A is not 0, then the column vectors of A are linearly independent. Next, I try to prove that statement A implies statement 10. A implies 10. So assume statement A, try to prove statement 10. So assume the column vectors of A are linearly independent. We try to prove that the column vector of A spans Rn. Let C1, C2, Cn be the column vectors of matrix A. Then the set of C1, C2, Cn is linearly independent. Since C1, C2, Cn, they have n components, since A has m rows, they are C1, C2, Cn, they all have n components, so they are all vectors in Rn. Since C1, C2, Cn, they are all vectors in Rn, then C1, C2, Cn is a subset in Rn. Since dimension of Rn is n, since dimension of Rn is n, and the set C1, C2, Cn is a linearly independent subset in Rn. With n vectors. Since dimension of Rn is n, and C1, C2, Cn is a linear independent subset in Rn with n vectors, then, according to a theorem in the earlier section, we know that the set C1, C2, Cn spans Rn. Then C1, C2, Cn spans Rn. That complete proof that A implies 10. If the column vectors of Rn are linearly independent, then the column vectors of A spans Rn. That complete proof that A implies 10. Next, let's prove that statement 10 implies statement 12. So, assume the column vectors of A spans Rn. We try to prove that the column vectors of A form a basis of Rn. Let's assume statement 10. Try to prove statement 12. Assume the column vectors of A span Rn. We try to prove that the column vectors of A form a basis of Rn. Assume the column vectors of A span Rn. Let C1, C2, Cn be the column vectors of A. Then the set C1, C2, Cn spans Rn. Hence, C1, C2, Cn is a subset of Rn. If C1, C2, Cn spans Rn, that means every C1, C2, Cn belongs to Rn. So C1, C2, Cn is a subset of Rn. We should prove that C1, C2, Cn is a basis of Rn. So let's try to show that they are linearly independent. Since dimension of Rn is n, and C1, C2, Cn is a subset of Rn. With n vectors. And C1, C2, Cn spans Rn. Then, according to a theorem in an earlier section, the set C1, C2, Cn, they are linearly independent. Since C1, C2, Cn spans Rn, and they are linearly independent, they form a basis in Rn. Let's complete the proof. 10 implies 12. If the column vector of A spans Rn, then the column vector of A form a basis of Rn. Next, let's try to prove that statement 12 implies statement 13. So we assume the column vectors of A form a basis of Rn. We try to prove that the row vectors of A also form a basis of Rn. Implies 13. So we assume the column vectors of A form a basis of Rn. Let C1, C2, Cn be the column vectors of A. And let R1, R2, Rn be the row vectors of A. Since A is an n by n matrix, A has n column vectors and n row vectors. Then, since the column vector of A span is form a basis of Rn, then span of C1, C2, Cn equal to Rn. And we know that span of C1, C2, Cn is the column space. So the column space of A equal to Rn. Hence, the dimension of the column space of A is the same as the dimension of Rn. They are equal to n. Then according to earlier theorem, we know that the dimension of a column space is always the same as the dimension of the row space. So the dimension of row space is also n. Since the dimension of the row space of matrix A is the same as dimension of column space of matrix A, that's the earlier theorem. Then the dimension of the row space of A is also n. Next, since the dimension of a row space of A is n, R1, R2, Rn is a subset in the row space. All row vectors are vectors in a row space. So R1, R2, Rn is a subset of the row space. And R1, R2, Rn spans the row space. The span of R1, R2, Rn is always a row space. So R1, R2, Rn spans the row space. Then, since the dimension of row space is n, R1, R2, Rn is a subset of the row space with n vectors, and R1, R2, Rn spans the row space. That means, according to earlier theorem, they must be linearly independent. Then R1, R2, Rn must be linearly independent. Since dimension of the row space is n, R1, R2, Rn is a subset of the row space with n vectors, and R1, R2, Rn spans the row space. That means R1, R2, Rn must be linearly independent. Next, since the dimension of Rn is n, and R1, R2, Rn is a linearly independent subset of Rn, since each R1, R2, Rn has n components, they are all vectors in Rn. So R1, R2, Rn form a subset of Rn, and we know that R1, R2, Rn they are linearly independent. So R1, R2, Rn is a linearly independent subset of Rn with n vectors. Then, according to the theorem in the earlier section, R1, R2, Rn they must span Rn. According to the theorem in the earlier section, R1, R2, Rn spans Rn. Since R1, R2, Rn they are linearly independent, and R1, R2, Rn spans Rn, that means R1, R2, Rn must be a basis in Rn. Hence, R1, R2, Rn form a basis in Rn. That complete proof that 12 implies 13. If the column vectors of A form a basis of Rn, then the row vectors of A also form a basis of Rn. Next, try to prove that statement 13 implies statement 11. Try to prove that statement 13 implies statement 11. Statement 13 says the row vectors of A form a basis of Rn. Try to prove that the row vectors of A span Rn. Next, 13 implies 11. Assume the row vectors of A form a basis of Rn. we try to prove that the row vectors of A spans Rn. That's obviously true. We know that a basis must be linearly independent. A must spans Rn. So it's true by the definition of basis. Then by the definition of a basis, the row vectors spans Rn. This is true by the definition of basis. A basis must be linearly independent. A must spans the vector space. So that's automatically true by the definition of basis. Next, we try to prove that statement 11 implies statement 9. Assume the row vectors of A spans Rn. We try to prove that the row vectors of A are linearly independent. 11 implies 9. So assume the row vectors of A spans Rn. We try to prove that the row vectors are linearly independent. Assume the row vectors of A spans Rn. We try to prove that the row vectors of A are linearly independent. Let R1, R2, Rn be row vectors of A. Then R1, R2, Rn spans Rn. Since dimension of Rn is n, R1, R2, Rn is a subset of Rn. With n vectors. Since each R1, R2, Rn has n components, so they are all elements of Rn, then R1, R2, Rn is a subset of Rn with n vectors. And R1, R2, Rn spans Rn. Then, by the theorem in the earlier section, if dimension of Rn is n, R1, R2, Rn is a subset of Rn with n vectors, then and R1, R2, Rn spans Rn, then this set R1, R2, Rn must be linearly independent. That complete the proof that if the row vectors of A spans Rn, then the row vectors of A are linearly independent. Next, we try to prove that statement 9 implies statement 7. Assume the row vectors of A are linearly independent. We try to show that determinant of A is not 0. Next, try to prove that statement 9 implies statement 7. So, assume the row vectors of A are linearly independent. We try to prove that the determinant of A is not 0. Let R1, R2, Rn be the row vectors of A. Then R1, R2, Rn, they are linearly independent. Which means, if I set K1, R1 plus K2, R2 plus Kn, Rn equal to 0, the only solution is that K1 equals 0, K2 equals 0, and Kn equals 0. The only solution to the above equation vector equation are K1 equals 0, K2 equals 0, Kn equals 0. Since R1, R2, Rn, they are linearly independent, the only solution to this vector equation is K1 equals 0, K2 equals 0, and Kn equals 0. Also, the augmentation matrix of an above vector equation can be written as the augmentation matrix of an above vector equation can be written as R1 in the first column, component of R1 in the first column, component of R2 in the second column, and component of Rn in the last column, in the nth column, and component of zero vector, component of the zero vector in the last column. And this augmentation matrix, in this augmentation matrix here, R1, R2, Rn, if I put row vectors in columns, that's A transpose. If I put row vectors in columns, this is A transpose. And above augmentation matrix can be written as A transpose times x equal to 0, where x is the column vector k1, k2, kn. If I put row vectors in columns, this is A transpose. We get A transpose times s equal to 0. since the only solution to the homogeneous linear system, this is a homogeneous linear system, A transpose x equal to 0 is x equal to 0. That's the trivial solution. Here, A is equal to 0 because K1 is 0, K2 is 0, Kn is 0. So x is the 0 vector, which is the trivial solution. Since the only solution to the homogeneous linear system is the trivial solution, then by equivalent statements, the matrix determinant of the matrix A transpose cannot be 0. Then determinant of A transpose cannot be 0. Since determinant of A is the same as determinant of A transpose, then determinant of A cannot be 0. That complete the proof that statement 9 implies statement 7. So you will complete the proof that statement 7 implies statement A. Statement A implies statement 10. 10 implies 12. 12 implies 13. 13 implies 11. 11 implies 9. 9 implies 7. That means statement 7 is equivalent to all these 6 statements. If all these 6 statements are equivalent to statement 7, and statement 7 are equivalent to all these 7 statements, all these 13 statements, they are equivalent. All these 13 statements are equivalent, which means if one of the statements is true, they are all true. If one of the statements is false, they are all false. Next, I will add 6 more statements to the equivalent statements. Statement 14 says A has rank n. Statement 15 says A has nullity of 0. Statement 16 says the kernel of T sub A is 0. And statement 17 says the range of T sub A is Rn. Statement 18 says T sub A is 1 to 1. Statement 19 says T sub A is on 2. We try to show that these 6 statements are equivalent to these 13 statements. So in order to prove that, I'll try to show that all these 6 statements are equivalent to statement 12. If they are all equivalent to statement 12, then all these 19 statements are equivalent. So I'll prove in the following way. I'll first of all show that statement 12 implies statement 19. Statement 19 implies statement 17. Statement 17 implies statement 14. Statement 14 implies statement 15. Statement 15 implies statement 16. And statement 16 implies statement 18. Then statement 18 implies statement 12. Next, let's first of all prove that statement 12 implies statement 19. 12 implies 19. So we first of all assume statement 12. Statement 12 says the column vectors of A form a basis of Rn. So we first assume the column vectors of A form a basis of Rn. We try to prove that T sub A is on 2 First of all, let A be the matrix A11, A12, A1n, A21, A22, A2n. Last row is AN1, AN2, and ANN. Let TA from Rn to Rn be the matrix transformation associated to matrix A. We try to show that TA is on 2. In order to show a function is on 2, we try to show that for every y in the codomain, there exists an x in the domain such that f of x equal to y. So let y equal to y1, y2, yn be a vector in the codomain. Here codomain is Rn. We try to show that there exists x in the domain such that t sub a of x equal to y. Now, let y be a vector in the domain. Since the column vectors of A form a basis of Rn, then y can be written as a linear combination of the column vectors. Then y equal to k1 times c1 plus k2 times c2 plus kn times cn, where c1, c2, cn are column vectors of A. And k1, k2, kn are scalars. Hence, k1 times c1 plus k2 times c2 plus kn times cn equal to y. So k1 times c1, c1 is the first column, a11, a21, an1 plus k2 times c2, c2 is the second column, a12, a22, an2 plus kn times cn. Cn is the last column. Altogether equal to y. Y is y1, y2, yn. Next, on the left side, if I distribute k1, k2, kn, what do I get? I get k1, a11. Let me write a11 first. I get a11, k1, a21, k1, and continue in the last row. I get an1, k1. That's the first column. Second column, distribute k2. I have a12, k2, A22 K2. And continue, I have AN2 K2. In the last column, I have A1N Kn, A2N Kn, ANN Kn. They equal to Y1, Y2, Yn. Next, on the left side, if I add this vector together, if I add this matrix together, I have A11 K1 plus A12 K2 plus A1N Kn in the first row. A21 K1 plus A22 K2 plus A2N Kn in the second row. And continue, I have AN1 K1 plus AN2 K2 plus ANN Kn in the last row. They equal to Y1, Y2, Yn. Here we can see that the left side can be written as the product of two matrices A11, A12, A1N, A21, A22, A2N, AN1, AN2, ANN times the column vectors K1, K2, Kn equal to Y1, Y2, Yn. The left side can be written as a product of two matrices. This matrix times this column vector. Then here, this matrix is the same as matrix A. So I have Ax equal to Y. Where X is the column vectors K1, K2, Kn. Here we have Ax equal to Y, where X is the column vectors K1, K2, Kn. Hence, left side As can be written as T sub A of X, because T sub A is the matrix transformation associated to A. So T sub A of X is the same as Ax. Here, X is a vector with n components that belong to Rn. So this X belongs to a domain. Since for all Y in the codomain, there is an X in the domain such that T of X is equal to Y, then T sub A must be onto. Since for all Y in the codomain, there exists an X in the domain such that T sub A of X equal to Y, then T sub A is onto. Let's complete the proof that statement 12 implies statement 19. Next, we try to prove that statement 19 implies statement 17. Statement 19 says T sub A is onto. We try to prove that the kernel of T sub A is Rn. We try to prove that the range of T sub A is Rn. This is true automatically by the definition of onto. The T sub A from Rn to Rn being a matrix transformation associated to A. Since T sub A is on 2, then by the definition of on 2, by the definition of on 2 function, the range of T sub A is the same as the codomain of T sub A. Since the codomain of T sub A is Rn, then the range of T sub A is Rn. Let's complete the proof that 19 implies 17. Next, we try to prove that 17 implies 14. Implies 14. Assume the range of T sub A is Rn. Let T sub A from Rn to Rn be the matrix transformation associated to matrix A. Let T sub A be the matrix transformation associated to A. Assume the range of T sub A is Rn. We try to prove that A has a rank of n. Since the range of T sub A is Rn, that means the dimension of the range of T sub A is the same as the dimension of Rn. According to earlier theorem, we know that the dimension of range of T sub A is the same as the dimension of a current space of A. According to earlier theorem, we know that the range of T sub A is the same as the range of T sub A is the same as the current space of A. So their dimension must be the same. So the range of T sub A is the same as current space of A. And dimension of Rn is n. Since range of T sub A is the same as current space of A, their dimension must be the same. And we know that dimension of Rn is n. And we know that dimension of a current space of A is the rank of A. Dimension of current space of A is the rank of A. So rank of A is n. Let's complete the proof that 17 implies 14. Next, we try to prove that 14 implies 15. So assume 14. Assume A has rank of k. A has rank n. We try to prove that A has nullity of 0. (14 implies 15). Assume A has rank of n. try to prove that A has nullity of 0. Assume A has rank of n. According to earlier theorem, we know that, according to the dimension theorem of matrices, we know that for any matrix A, its nullity plus its rank is always equal to n, where n is the number of columns in matrix A. Assume A has a rank of n. By the dimension theorem of matrices, rank of A plus nullity of A equal to n. Since rank of A is n, then nullity of A must be 0. That complete the proof that if A has a rank of n, then A must have nullity of 0. That complete the proof that 14 implies 15. Next, we try to prove that 15 implies 16. "15 says, assume A has nullity of 0, then the kernel of T sub A is 0. So here, first of all, let T sub A from Rn to Rn be the matrix formation associated to A. Assume the nullity of A is 0. We try to prove that the kernel of T sub A is 0. We know that nullity of A, by its definition, that's the dimension of the null space of matrix A. Then the dimension of the null space of matrix A is 0. And according to earlier theorem, we know that the null space of matrix A is in a sense the kernel of T sub A. So the dimension of the kernel of A, the dimension of the kernel of T sub A is 0. Since the dimension of kernel of T sub A is 0, then the kernel of T sub A must contains only one vector, contains only the 0 vector. Since the dimension of the kernel of T sub A is 0, then the kernel of T sub A contains only the 0 vector. Hence, the kernel of T sub A contains only the 0 vector. Since it has dimension 0, it contains only the 0 vector. That completes the proof that 15 implies 16. Next, we try to prove that 16 implies 18. 16 says the kernel of T sub A is 0. We try to prove that T sub A is 1-to-1. "16 implies 18. Assume the kernel of T sub A is 0. We try to prove that T sub A is 1-to-1. let T sub A from Rn to Rn be the matrix transformation associated to A. Assume the kernel of T sub A is 0. We try to prove that T sub A is 1 to 1. Let S1, S2 be two vectors in the domain. That's the domain Rn. Assume T sub A of S1 equal to T sub A of S2. We try to prove that S1 equal to S2. Then here, I can first of all move T sub A of S2 from right side to the left side. I have T sub A of S1 minus T sub A of S2 equal to 0. Since any matrix transformation is a linear transformation, this can be written as T sub A of S1 minus S2. Since every matrix transformation is a linear transformation, so this expression can be written as T sub A of S1 minus S2. Since the kernel of T sub A is 0, it contains only the 0 vector, and T sub A of this vector is 0. That means this vector here must be the 0 vector. Since the kernel of T sub A contains only the 0 vector, then the vector in the parentheses here must be the 0 vector. Since the kernel of T sub A contains only the 0 vector, then S1 minus S2 must be 0. Hence, S1 equal to S2. Since T sub A of S1 equal to T sub A of S2 implies S1 equal to S2, then T sub A must be 1 to 1. Hence, T sub A is 1 to 1. That completes the proof that 16 implies 18. Next, we try to prove that statement 18 implies statement 12. So we assume T sub A is 1 to 1. We try to prove that the column vectors of A form a basis of Rn. First of all, let T sub A from Rn to Rn be the matrix transformation associated to matrix A. Assume T sub A is 1 to 1. We try to prove that the column vectors of A form a basis of Rn. Let C1, C2, Cn be column vectors of A. Let C1, C2, Cn be the column vectors of A. Since A has m rows, each column vector has m components. Then each column vector is a vector in Rn. That means C1, C2, Cn is a subset in Rn. In order to show the column vector is a basis, we should show that they are linearly independent and they span Rn. In order to show that the column vectors C1, C2, Cn form a basis of Rn, we should show that these column vectors, they are linearly independent and they span Rn. First of all, we should show that C1, C2, Cn, they are linearly independent. So I first will set K1, C1 plus K2, C2 plus Kn, Cn equal to 0. Then this is a vector equation. Its augmentation matrix can be written in the following way. Then augmented matrix of this vector equation augmented matrix of the above vector equation can be written as component of C1 in the first column, component of C2 in the second column, and then continue component of Cn in the nth column, and the component of 0 in the last column. This is matrix A. C1 in the first column, C2 in the second column, Cn in the nth column. This is matrix A. This is a 0 vector. So the above augmented matrix can be written as Ax equal to 0. This is matrix A. X is K1, K2, Kn, where X is the column vectors K1, K2, Kn. So the above augmented matrix can be written as Ax equal to 0. This is matrix A. S is the column vector K1, K2, Kn, and that's 0. Last column is the 0 vector. Since T sub A is the matrix transformation associated to A, that means T sub A of X equal to A times X. Since TA is the matrix transformation associated to A, then TA of X equal to AX. Hence we have TA of X, T sub A of X equal to 0. Since any matrix transformation is a linear transformation, is a linear transformation, then T sub A of 0 equal to 0. So this 0 can be written as T sub A of 0. So T sub A of X equal to T sub A of 0, because this 0 is the same as T sub A of 0. Then since T sub A is 1 to 1, then if T sub A of X equal to T sub A of 0, what in the parentheses must be the same. Then S equal to 0. Hence, if S is 0, that means K1 is 0, K2 is 0, and Kn is 0. If S is the 0 vector, that means K1 is 0, K2 is 0, and Kn is 0. Since the only solution to this vector equation is K1 equals 0, K2 equals 0, and Kn equals 0, that means the column vectors C1, C2, Cn, they must be linearly independent. So the column vectors C1, C2, Cn, they must be linearly independent. Next, since dimension of Rn is n, and the column vectors C1, C2, Cn is a linearly independent subset of Rn. Since C1, C2, Cn is a subset of Rn, and they are linearly independent, so that's a linearly independent subset of Rn with n vectors. Then, according to the signal in the earlier section, we know that if dimension of a vector space is n, and C1, C2, Cn is a linearly independent subset of Rn with n vectors, then this set must span the vector space. Then C1, C2, Cn span Rn. Hence, it's a basis of Rn. Since they are linearly independent and it spans Rn, it must be a basis of Rn. Hence, C1, C2, Cn is a basis of Rn. Form a basis of Rn. Let's complete the proof that if T sub A is 1 to 1, then the column vectors of A form a basis of Rn. So all these 6 statements are equivalent to statement 12. All these 6 statements are equivalent to statement 12. That means all these 19 statements are equivalent. If one of the statements is true, then all statements are true. If one of the statements is false, then all statements are false. Hello everyone. Today we will study eigenvalues and eigenvectors. First of all, let me introduce what is an eigenvalue and what is an eigenvector. Let A be an n by n matrix, and let X be a non-zero vector in Rn. If A times X equal to some multiple of X, if A times X equal to some multiple of X, which means AX equal to lambda X for some scalar lambda, then this scalar lambda is called eigenvalue of A. And this non-zero vector X is called eigenvector corresponding to lambda. That's what eigenvalue and eigenvector means. Next, let me show you how to find eigenvalues and eigenvectors. Let me show you how to find eigenvalues first. So first of all, let A be an n by n matrix. How can we find eigenvalues of A? we know that an eigenvalue must satisfy this equation, AX equal to lambda x. An eigenvalue lambda must satisfy this equation, AX equal to lambda x. In this equation, I can move AX from left side to the right side. So I get 0 equal to lambda x minus AX. Next, for the first term, x is an n by 1 column vector. X is an n by 1 column vector. X can be written as I times x minus AX. This x can be written as I times x. This column vector x can be written as I times x. Next, on the right side here, I can factor x out. I get lambda I minus A equal to times 0. I get 0 equal to lambda I minus A times x. And this equation can be written as, it can be rewritten as lambda I minus A times x equal to 0. This is an n by n matrix. X is an n by 1 column vector. 0 is also n by 1 column vector. So this equation here can be considered as a homogeneous linear system of equations. Then, by an equivalent statements, if the determinant of this square matrix is not 0, the homogeneous system of equation has only the trivial solution. Trivial solution means x must be 0. Then s must be 0. If the determinant of this matrix is not 0, the homogeneous system has only the trivial solution, which means x must be 0. If s is 0, then lambda cannot be an eigenvalue. If s is 0, then lambda cannot be an eigenvalue, because here x must be a non-zero vector for lambda to be eigenvalue. If s is 0, then lambda cannot be an eigenvalue. So lambda is no eigenvalue of A. On the other hand, if determinant of lambda I minus A is 0, if the determinant of lambda I minus A is 0, then the homogeneous system has non-zero solutions. Then there exists non-zero vector x which satisfies this equation. Then lambda is an eigenvalue. In this case, lambda is an eigenvalue. Lambda is an eigenvalue of A. So, if the determinant of lambda I minus A is not 0, then lambda is not eigenvalue of A. But if determinant of lambda I minus A is 0, then lambda is an eigenvalue of A. So, based on this, we have the following theorem. The theorem says, let A be an n by n matrix. Then lambda is an eigenvalue of A if and only if determinant of lambda I minus A equals 0. According to this theorem, if we want to find eigenvalues of a matrix A, we set the determinant of lambda I minus A equal to 0, and then solve this equation for lambda. All solutions to this equation is an eigenvalue of A. So that's how we find eigenvalues of a matrix. In the above theorem, the equation determinant of lambda I minus A equals 0. This equation is called a characteristic equation of A. And the expression itself without equal sign, determinant of lambda I minus A, this is called a characteristic polynomial of A. Keep this terminology in mind. Next, let's look at some simple examples. Let A be a 2 by 2 matrix, 2, 4, 5, 3. Find the eigenvalue of A. So, according to this theorem, if we want to find eigenvalues, we first of all set determinant of lambda I minus A equals 0. So let's find lambda I minus A first. What's lambda I minus A? I is a 2 by 2 matrix. Here, since A is 2 by 2, I is also 2 by 2. I is a 2 by 2 matrix. 1, 0, 0, 1. A is a matrix. 2, 4, 5, 3. So the first part can be written as lambda 0, 0, lambda if I distribute lambda plus distribute negative sign. I get negative 2, negative 4, negative 5, negative 3. Then adding up, we get lambda minus 2, negative 4, negative 5, lambda minus 3. That's lambda I minus A. Next, take determinant, set equal to 0. Determinant of lambda I minus A is the determinant of this matrix. This is a 2 by 2 matrix. For the determinant, there's a shortcut. I get lambda minus 2 times lambda minus 3 minus 4 times 4 is 20. That's the characteristic equation. That's a characteristic polynomial. Next, simplify. We get lambda minus 5, lambda square minus 5 lambda plus 6 minus 20. Combine like terms. We get lambda square minus 5 lambda minus 14. That's the characteristic polynomial in a simplified form. Next, set equal to 0. Solve an equation for lambda. This equation can be factored as x minus 7 times s plus 2 equal to 0. Solve an equation, lambda is 7 and lambda is negative 2. They are called eigenvalues of matrix A. They are called eigenvalues of matrix A. But how can we find eigenvectors? Those are eigenvalues. Next, how can we find eigenvectors? We know that for each eigenvalue lambda, there is an eigenvector x such that ax equal to lambda x. And also we know that the first equation here is equivalent to the last equation, which means for each eigenvalue lambda, there is an eigenvector x which satisfies this equation. And also we know that an eigenvector cannot be 0. It must be a non-zero vector. This is a homogeneous linear system of equations. For each lambda, this is a homogeneous linear system of equations. If it has a non-zero solution, that means it has infinitely many solutions. If it has a non-zero solution, that means it has infinitely many solutions. And we know that all these solutions form a vector space, which is the solution space of this homogeneous system of equations. This solution space is called Eigen Space, corresponding to lambda. This solution space is called Eigen Space. It's called Eigen Space, corresponding to lambda. Next, let me introduce the Eigen Space. Let A be an n by n matrix. Then, for each eigenvalue lambda, the solution space of the homogeneous linear system of equations, lambda I minus A times S equal to 0. It's called an Eigen Space corresponding to lambda. And all vectors in the solution space is called eigenvector corresponding to lambda. All non-zero vectors in the solution space is called eigenvector corresponding to lambda. All non-zero vectors in the eigenspace is called the eigenvectors corresponding to lambda. So here you can see that for each eigenvalue lambda, there exists infinitely many corresponding eigenvectors, and all its corresponding eigenvectors belong to the eigenspace corresponding to lambda, which is the solution space of the homogeneous system, lambda I minus A times S equals 0. Next, let's look at some examples. In the previous example, find all linearly independent eigenvectors for each eigenvalue. Since for each eigenvalue there exists infinitely many corresponding eigenvectors, we are only looking for linear independent eigenvectors. In the previous example, there are two eigenvalues, lambda equals 7 and lambda equals -2. Let's find the eigenvectors for lambda equals 7 first. When lambda is 7, all eigenvectors belong to the solution space of this homogeneous system, lambda I minus A times S equals 0. So I first of all plug in 7 for lambda. If I plug in 7 for lambda, I have 7I minus A. Here, lambda I minus A is this matrix. If I plug in 7 for lambda, I plug in 7 here. I get 7 minus 2, -4, -5, and 7 minus 3. So lambda is 7. For lambda I minus A, I plug in 7, I plug 7 into this matrix. I get 7 minus 2 is 5. -4 stays the same. -5 stays the same. 7 minus 3 is 4. That's this matrix, lambda I minus A. And its augmented matrix. For its augmented matrix, I have for its augmented matrix, I write the first matrix, lambda I minus A first. I get 5, -4, -5, and 4, followed by the 0 vector, That's an augmented matrix of this homogeneous system, lambda I minus A times S equals 0. Next, solve the system using the Gauss-Jordan Elimination. We can see that in the first row, second row, the coefficient is almost the same, but I have opposite operation. To make it easier, I can directly add the first row to the second row. To make it easier, I can directly add the first row to the second row. Take R1 plus R2. Since all coefficients are the same, but I have opposite sign, I can directly add the first row to the second row. I get 5, negative 4. Negative 4, 0 in the first row, and 0, 0, 0 in the second row. Next, we try to make a leading one in the first row. So I can divide first row by 5. Take 1/5 times row 1. I get 1, negative 4 over 5, 0, and 0, 0, 0 in the second row. That's in the reduced Rorschach form. Next, rewrite the first row back to equation. I have S1 minus 4 over 5 S2 equal to 0. Here, in the first column, there's a leading one, so S1 is a leading variable. In the second column, there's no leading one. That means S2 is a free variable. So I write leading variable in terms of free variable. I get S1 equal to 4 over 5 times S2. Here, since S2 is a free variable, let S2 be T. Then all solutions S1, S2 can be written as 4 over 5 times T, and S2 is T. Next, factor T out. I get 4 over 5 and 1. This is the basis of the solution space. This is the basis of the solution space, which is the basis of the Eigen Space, which is the basis of the Eigen Space. So the Eigen Space is the span of this vector. All vectors in the span are called eigenvectors. All non-zero vectors in the span are called eigenvectors. Since there's only one vector in the basis, all vectors in the span must be a constant multiple of this vector. So for linear independent eigenvector, it could be any multiple of this vector. To make it easier, we try to use whole numbers. So I can multiply this vector by 5. To make it easier, we prefer to use whole numbers. So I can multiply this vector by 5. If I multiply this vector by 5, I get 5 times 4 over 5, comma 1, which is 4, comma 5. That's a linear independent eigenvectors for this eigenvalue lambda equals 7. Next, find eigenvector for lambda equal to negative 2. Do the same thing. When lambda equal to negative 2, let's find augmentation matrix for this homogeneous system first. So for this homogeneous system, for the augmentation matrix of this homogeneous system, a shortcut is we plug in lambda, then set equal to 0. A shortcut is plug in lambda, and then set equal to 0. That's an augmentation matrix of this homogeneous system. Lambda I minus A times S equal to 0. Plug in lambda, and then set equal to 0, 0. When lambda is negative 2, if I plug in negative 2 for each lambda, negative 2 minus 2 is negative 4. Negative 4 stays the same. Negative 5 stays the same. Negative 2 minus 3 is also negative 5. That's the matrix. Lambda I minus A. And then for the augmentation matrix, I add 0. I add 0 vector in the last column. H0 vector in the last column. That's the augmentation matrix of this homogeneous system. Lambda I minus A times S equal to 0. Next, solve it using the Gauss-Jordan Elimination. I can first of all divide first row by -4, make leading one here. I get 1, 1, 0. Leave second row the same. Next, I can multiply first row by 5, add it to the second row. Multiply first row by 5, add it to the second row. I get 1, 1, 0, 0, 0, 0. That's in the reduced low echelon form. Next, rewrite the first row back to equation. Rewrite the first row back to equation. I have S1 plus S2 equal to 0. Here, in the first column, there's a leading one. So S1 is a leading variable. In the second column, there's no leading one. This is no leading one. In the second column, there's no leading one. So S2 is called free variable. Write the leading variable in terms of free variable. I get S1 equal to negative S2. Since S2 is a free variable, let S2 equal to T. Then the solution S1, S2 can be written as S1 is negative T, S2 is T. Next, if I factor T out, I get -1 and 1. This is the basis of the solution space, which is also the basis of an Eigen space. So the Eigen space is the span of this vector. -1, 1. Eigen space is the span of this vector. -1, 1. And all non-zero vectors in the span are eigenvectors corresponding to lambda equal to -2. So a linear independent eigenvector could be any multiple of these vectors. Make it easier, I use the vector itself. Since all components are whole numbers, I can use the vector itself. -1, 1. That's a linear independent eigenvectors corresponding to lambda equal to -2. So that's how we find linear independent eigenvectors. Next, let me show you more examples. Find the eigenvalues for each of the following matrices, and find all linearly independent eigenvectors for each eigenvalue. First example, we have a 2 by 2 matrix, 3, 1, -1, 5. Let's find the eigenvalue first. In order to find the eigenvalue, let's first find the matrices. Lambda I minus A. Here, A is a 2 by 2 matrix. That's a 2 by 2 matrix. So I is 1, 0, 0, 1. Minus the matrix itself. 3, 1, -1, 5. If I distribute lambda, I get lambda 0, 0, lambda. If I distribute -1, I get -3, 1, -3, -1, 1, -5. Then add them up. I get lambda minus 3, -1, 1, lambda minus 5. Next, find the determinant of this matrix. That's the characteristic polynomial. Find the determinant of this matrix. Lambda I minus A. That's the characteristic polynomial. This is a 2 by 2 matrix. Its determinant is lambda minus 3 times lambda minus 5 minus -1. If we simplify and combine like terms, that's lambda squared minus A lambda minus 15 plus 1, which is lambda squared minus a lambda plus 16. Next, set the characteristic polynomial equal to 0. Set lambda square minus a lambda plus 16 equal to 0. That's called a characteristic equation. If we set the characteristic polynomial equal to 0, that's called a characteristic equation. Next, solve an equation for lambda. This equation can be factored as lambda minus 4 square. Then solve for lambda. Here, lambda equal to 4. That's an eigenvalue. In this matrix, there's only one eigenvalue. Next, we find an eigenvector for this eigenvalue. When lambda equal to 4, we first of all plug in 4 into the matrix, lambda I minus a. I get 1, negative 1, 1, negative 1. Next, set this matrix equal to 0. That's the augmentation matrix of the equation lambda I minus a times s equal to 0. That's the augmentation matrix of this equation, of this homogeneous system. Next, solve an equation using the Gauss-Jordan Elimination. Solve the equation using the Gauss-Jordan Elimination. There's a leading one here in the first row, so I can multiply first row by negative 1, add it to the second row. I get 1, negative 1, 0. Second row is 0, 0, 0. That's in the reduced low echelon form. Next, change the first row back to equation. I have x1 minus s2 equal to 0. Here, in the first column, there's a leading 1. That means s1 is a leading variable. In the second column, there's no leading 1. That means s2 is a free variable. So next, we get a leading variable, write a leading variable in terms of free variable. I get s1 equal to s2. Write a leading variable in terms of the free variable. Since s2 is a free variable, next, I let s2 equal to t. Then the solution, s1, s2 can be written as s1 is s2, which is t. s2 itself is also t. Next, I can pull out t. I get 1, 1. This vector is in the basis. That's the basis of the solution space. This vector 1, 1 is the basis of the solution space, which means the eigenspace is spanned by this vector. The eigenspace is spanned by this vector. The eigenspace is spanned by this vector. 1, 1. So that's an eigenspace. And we know that all non-zero vectors, every non-zero vectors in the eigenspace is an eigenvector. Every non-zero vectors in the eigenspace is an eigenvector corresponding to lambda equal to 4. Here, since there's only one vector in the basis of an eigenspace, there's only one linear independent eigenvector, which could be any multiple of this vector. Make it easier, I choose eigenvector to be the vector itself, 1, 1. So that's the linear independent eigenvector corresponding to lambda equal to 4. In this example, there's only one eigenvalue, and there's only one linear independent eigenvector. Next example, we have a 3 by 3 matrix. Let's try to find an eigenvalue and eigenvector using the same procedure. First of all, let's find the matrix, lambda I minus a. Here, since A is a 3 by 3 matrix, I must be 1, 0, 0, 0, 1, 0, and 0, 0, 1. And A is a matrix 3, negative 1, negative 1, 2, 0, negative 2, 0, 0, 2. If we distribute lambda, we get lambda 0, 0, 0, lambda 0, 0, 0, lambda. If we distribute negative sign, we get negative 3, 1, 1, negative 2, 0, 2, 0, 0, negative 2. Then add the matrix together, we get lambda minus 3, 1, 1, negative 2, lambda 2, 0, 0, lambda minus 2. Next, find a characteristic polynomial, which is the determinant of this matrix, lambda I minus A. That's the characteristic polynomial. This is a 3 by 3 matrix. In order to find the determinant, we must use cofactor expansion. In order to find the determinant, we must use cofactor expansion. Here in the last row, there's only one entry here. There's only one non-zero entries. So you can find cofactor expansion along the last row. For cofactor expansion, the sign is always plus, minus, plus, minus, plus, minus, plus, minus, plus. So in the last row, in the last entry here, the sign is positive. That's positive lambda minus 2 times determinant of the submatrix. By crossing out the last row, last column, we have determinant of this matrix. Lambda minus 3, 1, negative 2 times lambda. That's lambda minus 2 times determinant of this 2 by 2 matrix. That's lambda times lambda minus 3 minus negative 2. That's lambda minus 2 times lambda square minus 3 lambda plus 2. Then factor. Lambda square minus 3 lambda plus 2 can be factored as lambda minus 2 times lambda minus 1, which can be written as lambda minus 2 square times lambda minus 1. That's the characteristic polynomial in the factor form. Next, we set the characteristic polynomial to 0. That's the characteristic equation. Next, solve the characteristic equation. We get lambda equal to 2 and lambda equal to 1. So we have 2 eigenvalues. In this example, we have 2 eigenvalues. Next, find eigenvectors for each eigenvalue. When lambda equal to 2, I first of all plug in 2 into the matrix, lambda I minus A. So plug in 2 here. If I plug in 2, what do we get? If we plug in 2 here, 2 minus 3 is negative 1. 1 and 1 stays the same. In the second row, I get negative 2, 2, 2. In the third row, I get 0, 0, 0. That's the matrix when I plug in lambda. Next, we need to find the augmentation matrix of the equation. Lambda I minus A times S equal to 0. For the augmentation matrix of this equation, a shortcut is take the matrix lambda I minus A, add 0 at the end, add a 0 vector at the end. That's an augmentation matrix of this equation, lambda I minus A times S equal to 0. Next, solve this equation using the Gauss-Jordan Elimination. First of all, we try to make a leading one in the first row. So I can multiply first row by negative 1, which is 1, negative 1, negative 1, 0. Leave the second row the same. I get negative 2, 2, 2, 0. Leave the third row the same. Next, that's the leading one. We try to make it first. I try to make everything under leading one to be 0. So I multiply first row by 2, add it to the second row. Multiply first row by 2, add it to the second row. I get 1, negative 1, negative 1, 0. 0, 0, 0 in the second row, 0, 0, 0 in the third row. That's in the reduced lower echelon form. Next, rewrite the first row back to equation. I have S1 minus S2 minus S3 equals 0. In this equation, S1 is a leading variable. And in the second column, third column, for S2, S3, there's no leading one. That means X3, S2, S3, they are free variables. Next, in this equation, write the leading variable in terms of a free variable. I get S1 equal to S2 plus S3. Write the leading variable in terms of the free variables. Here, since S2, S3 are free variables, we pick two variables for S2, S3. So next, let S2 equal to T, X3 equal to S. Then the solution, S1, S2, X3 can be written as S1 equal to S2 plus X3, which is T plus S. S2 is T, X3 is S. There are two variables, S and T. Next, I write T in a column, write S in a different column. I have T, T0 in the first column, plus S0, S in the second column. Write this in two columns. Write this column in two columns. Put T in the first column, S in the second column. Next, pull out S, pull out T. I get T times the vector 1, 1, 0, plus S times the column vector 1, 0, 1. These two vectors are the basis of the solution space. These two vectors are the basis of the solution space. So the Eigen space is spanned by these two vectors. So for lambda equal to 2, the corresponding Eigen space is spanned by these two vectors. Eigen space is spanned by these two vectors, 1, 1, 0, and 1, 0, 1. Eigenvector is any non-zero vectors in the eigenspace spanned by these two vectors. Since there are two vectors in the basis, there exist two linear independent eigenvectors. It could be any multiple of these two vectors. So I pick S1 to be 1, 1, 0. I pick S2 to be 1, 0, 1. Those are two linear independent eigenvectors corresponding to this lambda equal to 2. So for lambda equal to 2, there are two linear independent eigenvectors. Next, find eigenvector when lambda equal to 1. Find eigenvector when lambda equal to 1. When lambda equal to 1, we plug in 1 into the equation, into the matrix lambda I minus A. If we plug in 1, 1 minus 3 is negative 2. 1 stays the same. Negative 2 stays the same. 1, 2. 0, 0. If we plug in 1 here, 1 minus 2 is negative 1. Next, set this equal to 0. That's the augmentation matrix of the equation. Lambda I minus A times S equal to 0. That's the augmentation matrix of this equation. Next, reduce the matrix using the Gauss-Jordan Elimination. Here, in the first row, try to make negative 2 to be the leading one. The only choice for us is divide the first row by negative 2. I get 1, negative half, 0. Leave the second row the same, negative 2, 1, 2, 0. Third row is 0, 0, negative 1, 0. That's the leading one here. Next, I can multiply first row by 2, add it to the second row. I get 1, negative half, 0, 0, 1, 0, 0, negative 1. Next, in the second row, that's the leading one here. We try to make all entries above and below leading one to be 0. So I can first of all multiply the second row by a half, add it to the first row. I get 1, negative half, 0, 0, 0, 0, 1, leave the second row the same. Then I can directly add the second row to the third row. I get 0, 0, 0, 0. That's in the reduced row echelon form. Next, run the first two rows. Back to equation. I have S1 minus half S2 equal to 0. And we have X3 equal to 0. Since in the first column, in the third column, there's a leading 1. That means X1, X3, they are leading variables. In the second column, there's no free variable. There's no leading 1. That means S2 is a free variable. In the second column, there's no leading 1. That means S2 is a free variable. Next, write the leading variables in terms of the free variable. I have S1 equal to half of S2. X3 equal to 0. Write the leading variable in terms of the free variable. Here, since S2 is a free variable, next we let S2 be T. Next, let S2 be T. If I let S2 be T, the solutions S1, S2, X3 can be written as S1 is half of S2, which is half of T, since S2 is T. So that's half of T. S2 itself is T. X3 is 0. X3 is 0. There's only one variable. Next, I can pull out T. If I pull out T, I get half 1, 0. That's the basis of an eigenspace. That's the basis of an eigenspace. So an eigenspace is the span of this vector. Half 1, 0. And an eigenvector could be any non-zero vector in the eigenspace. Here, since there's only one vector in the basis of an eigenspace, there's only one linearly independent eigenvector. An eigenvector could be any multiple of this vector in the basis. Half 1, 0 could be any multiple of this vector. In order to make it easier, we try to use whole numbers for an eigenvector. So I can multiply this vector by 2. Since the eigenvector could be any multiple of this vector in the basis. If I multiply this vector by 2, I get 1, 2, 0. So that's a linear independent eigenvector for lambda equal to 1. That's a linear independent eigenvector corresponding to lambda equal to 1. So together we have 3 eigenvectors. We have 3 linear independent eigenvectors. Next example, we have a 3 by 3 matrix. We try to find the eigenvalues and all linear independent eigenvectors for each eigenvalue. Let's find the eigenvalue first. First one, let's compute the matrix lambda I minus A. Here, since A is a 3 by 3 matrix, I must be 1, 0, 0, 0, 1, 0, 0, 0, 1, minus A. A is the matrix 1, negative 5, 3, negative 1, 1, 1, negative 2, 2, 2. Next, let's multiply. If I multiply lambda, I get lambda 0, 0, 0, lambda 0, 0, 0, lambda. Distribute negative sign. I get 1, negative 1, 5, negative 3, 1, negative 1, negative 1, 2, negative 2, negative 2. Then adding up. Together I get lambda minus 1, 5, negative 3, 1, lambda minus 1, negative 1, 2, negative 2, and lambda minus 2. Next, find a characteristic polynomial, which is the determinant of this matrix, lambda I minus A. So this is a 3 by 3 matrix. Here we must use a cofactor expansion. Since there are no zeros, Let me take cofactor of expansion around the first row. The sign is plus, minus, plus, minus, plus, minus, plus, minus, plus. So in the first row, the sign is plus, minus, plus. So first one is positive. We get lambda minus 1 times determinant of the determinant of the submatrix. Lambda minus 1, negative 1, negative 2, lambda minus 2, minus 5 times determinant of the submatrix. 1, negative 1, 2, lambda minus 2, plus negative 3 times determinant of the submatrix. 1, lambda minus 1, 2, negative 2. Then multiply out. We get lambda minus 1 times lambda minus 1 times lambda minus 2 minus 2 minus 5 times lambda minus 2 minus negative 2 minus 3 times negative 2 minus 2 times lambda minus 1. Then simplify. We have lambda minus 1 times lambda square minus 3 lambda plus 2 minus 2 can cancel, minus 5 times lambda minus 2 plus 2, that's lambda, minus 3 times negative 2 times negative 2 lambda plus 2. Negative 2 cancels positive 2, we get negative 2 lambda. Then distribute, we get lambda cube minus 3 lambda square minus lambda square plus 3 lambda minus 5 lambda plus 6 lambda. Then combine like terms, we get lambda cube minus 4 lambda square. 3 lambda minus 5 lambda is negative 2 lambda. Negative 2 lambda plus 6 lambda is 4 lambda. Next, we can factor. If I pull out lambda, I get lambda square minus 4 lambda plus 4. Keep factoring, we get lambda times lambda minus 2 square. That's the characteristic polynomial in a factor form. Next, we set a characteristic polynomial to 0. Set a characteristic polynomial to 0. We get lambda times lambda minus 2 squared equal to 0. That's called a characteristic equation. Next, solve an equation for lambda. We get lambda equal to 0 and lambda equal to 2. We have two eigenvalues, lambda equal to 0 and lambda equal to 2. Eigenvalue could be 0, but eigenvector cannot be 0. Eigenvalue could be 0, but eigenvector cannot be a 0 vector. Be very, very careful. So next, for each eigenvalue, let's find the corresponding eigenvectors. When lambda is 0, we plug 0 into the matrix lambda I minus A. If I plug in 0, I get negative 1, 5, negative 3 in the first row. Negative 1, 5, negative 3 in the first row. If I plug in 0, I get 1, negative 1 in the second row. If I plug in 0, I get 2, negative 2 in the third row. Then, for the augmented matrix of the equation, lambda I minus A times x equal to 0. For the augmented matrix of this equation, I take this matrix followed by a 0 vector, 0, 0, 0, set each row equal to 0. Then, solve this equation using the Gauss-Jordan Elimination. First step, we try to make a leading one here. So I can interchange row 1 and row 2. I get 1, -1, -1, 0 in the first row, -1, 5, -3 in the second row, 2, -2, -2 in the third row. That's a leading one. We try to make all entries below leading one to be 0. So I can directly add the first row to the second row. Row 1 plus row 2. First row stays the same, 1, -1, -1, 0. Second row becomes 0, 4, -4, 0. Next, I can multiply first row by -2, add it to the third row. I can multiply first row by -2, add it to the third row. I get 0, 0, 0, 0. Next, go to the second row. Try to make the first non-zero entry to be a 1. So I can divide second row by 4. If I divide second row by 4, first row stays the same, 1, -1, -1, 0. Second row becomes 0, 1, -1, 0. 0, 0, 0, 0. Next, there's a leading one here. We try to make all entries above and below leading one to be 0. So I can add second row to the first row. Next, add second row to the first row. I get 1, 0, -2, 0. 0, 1, -1, 0. Next, run the first row and second row back to equation. This is in the reduced echelon form. Next, run the first row and second row back to equation. I get S1 minus 2S3 equals 0. S2 minus X3 equals 0. Here, in the first column and second column, they are leading ones. In the first column and second column, they are leading ones. That means S1, S2, they are leading variables. But in the third column, there's no leading one. That means X3 is a free variable. So X3 is a free variable. Next, run a leading variable in terms of a free variable. I get S1 equal to 2x3. S2 equal to S3. Run a leading variable in terms of a free variable. Since X3 is a free variable, next, let X3 be T. If I let S3 be T, then the solution S1, S2, S3 can be written as S1 equal to 2T, S2 equal to T, X3 itself is T. There's only one variable, T. Next, I can pull out T. If I pull out T, I get 2, 1, 1. That's the basis of the solution space, which is also the basis of an eigenspace. So an eigenspace is spanned by this vector. Eigenspace is spanned by this vector. An eigenvector could be any non-zero vector in the eigenspace. Since there's only one vector in the basis of an eigenspace, there's only one linearly independent eigenvector. And this eigenvector could be any multiple of this basis vector. Since all entries are whole numbers, we can leave in the VTs. So that's an eigenvector corresponding to lambda equals 0. That's a linearly independent eigenvector corresponding to lambda equals 0. Next, when lambda equals 2, we plug in 2 into this matrix, lambda I minus A. Plug in 2 here. When lambda equals 2, plug 2 into this matrix. 2 minus 1 is 1, so the first row is 1, 5, -3. Next, plug in 2. 2 minus 1 is 1, so second row is 1, 1, -1. In the third row, if I plug in 2 here, 2 minus 2 is 0, so the third row is 2, -2, 0. Next, for the augmentation matrix of this equation, we add 0 in the last column. That's the augmentation matrix of this equation. Next, solve the equation using the Gauss-Jordan Elimination. That's a leading one here. We try to make all entries below leading one to be 0. So I can multiply first row by -1, add it to the second row. I get 1, 5, -3, 0. 0, -4, 3 plus -1 is 2, 0. Next, I can multiply first row by -2, add it to the third row. I get 0, -12, +6, 0. Next, in the second row, try to make the first non-zero entry to be a 1. The only possibility for us is divide second row by -4. Divide second row by -4. So first row is 1, 5, -3. Second row is 0, 1, -half. Next, try to make 0, leave the third row the same. I get 0, -12, 6, 0. Next, let the leading one in the second row. We try to make all entries above and below leading one to be 0. Next, I can multiply second row by -5, add it to the first row. I get 0, 1, 0, 5/2 plus -3 is -1/2, 0. Leave the second row the same. I get 0, 1, -1/2, 0. Next, I can multiply second row by 12, add it to the third row. I get 0, 0, 0, 0. That's in the reduced lower echelon form. Next, rewrite the first row and second row back to equation. Rewrite the first row and second row back to equation. First row can be written as S1 minus half x3 equals 0. Second row can be written as S2 minus half x3 equals 0. Here, in the first two columns, they are leading ones, which means S1, S2, they are leading variables. In the third column, there are no leading ones, which means x3 is a free variable. In the third column, there's no leading ones. That means x3 is a free variable. So next, write a leading variable in terms of a free variable. I have S1 equal to half of x3 and S2 equal to half of S3. Since x3 is a free variable, next, I let x3 be t. Then the solution, S1, S2, S3 can be written as S1 is half of t. S2 is also half of t. X3 itself is t. Next, pull out t. If I pull out t, I get half, 1. That's the basis of the solution space, which is also the basis of the eigenspace. So the eigenspace is spanned by this vector. The eigenspace is spanned by this vector. So here, every non-zero vector in the eigenspace is an eigenvector corresponding to lambda equal to 2. And here, since in the basis of an eigenspace, there's only one vector, which means there's only one linearly independent eigenvector. And this eigenvector could be any multiple of the basis vector. It could be any multiple of this vector in the basis. In order to make it easier, we prefer to use whole numbers for eigenvectors. So I can multiply this basis vector by 2. If I multiply this vector by 2, I get 1, 1, 2. So that's a linear independent eigenvector corresponding to lambda equal to 2. So for this matrix, together we have two eigenvalues and two linear independent eigenvectors. We have two eigenvalues and two linear independent eigenvectors. Next, let's create a theorem. Let A be an n by n matrix. Then lambda equals 0 is the eigenvalue of A if and only if determinant of A is 0. What does this theorem mean? In the previous example, lambda equals 0 is the eigenvalue of the matrix. In the matrix here, we can see that the third row is the multiple of the second row. If I multiply the second row by 2, I get a third row. We know that in a matrix, if a row is a multiple of another row, the determinant of the matrix must be 0. So that's an example that lambda equals 0 is the eigenvalue if and only if determinant of the matrix is 0. But an example is not proof. How can we prove the theorem here? This theorem is in the form of if and only if. In general, when we try to prove a theorem in the form of if and only if, we try to prove that left side implies the right side, and right side implies the left side. That's one way to prove the statement in the form of if and only if. Another way to prove the theorem in the form of if and only if is that I can prove P implies Q, and not P implies not Q. That means P and Q are either both true or both false. That's another way to prove the statement in the form of if and only if. So for this theorem, I'll prove in this way. I first assume lambda is 0, lambda equals 0 is the eigenvalue of A. Then try to prove that determinant of A is 0. Next, I assume lambda equals 0 is not eigenvalue of A. And I try to prove that determinant of A is not 0. So let's first assume lambda equals 0 is the eigenvalue of A. Let's first assume lambda equals 0 is the eigenvalue of A. Which means if I plug in 0 for lambda in a characteristic polynomial, I must get 0. If 0 is eigenvalue of A, then if I plug in 0 into the characteristic polynomial, I must get 0. Which means determinant of negative A is 0. And we know that for determinant of a constant times the matrix, that's k to the power n times determinant of A. Assume A is n by n matrix. Determinant of Ka is always k to the power n times determinant of A. Here, determinant of negative A can be written as determinant of negative 1 times A. Then if I pull out negative 1, I get negative 1 to the power A to the power n times determinant of A. And negative 1 raised to any power is not 0. So I can divide both sides by negative 1 to the power n. So determinant of A is 0. Here I assume lambda is 0, lambda equals 0 is the eigenvalue of A. And I prove that determinant of A is 0. That's P implies Q. Next, I should prove that not P implies not Q. So next, assume lambda equals 0 is not eigenvalue of A. That means if I plug in 0 into the characteristic equation, I won't get 0. If I plug in 0 into the characteristic polynomial, I won't get 0. So if I plug in 0 for lambda, I get 0 times I minus A. It won't be 0. If 0 is no eigenvalue of A, when I plug in 0 into the characteristic polynomial, I won't get 0. So that means determinant of negative A is not 0. Next, I can pull out negative 1. I get negative 1 to the power n times determinant of A is not 0. If the product of two numbers is not 0, that means none of them can be 0. If the product of two numbers is not 0, that means none of them could be 0. So determinant of A cannot be 0. That complete the proof that not P implies not Q. So P implies Q, not P implies not Q. That means these two statements, they're either both true or both false. That means lambda is 0, lambda equal to 0 is eigenvalue of A, if and only if determinant of A is 0. Next, let's go back to the equivalent statement. According to the previous theorem, I can add one more statement to the equivalent statements. Statement 20. Lambda equal to 0 is not eigenvalue of A. According to the previous theorem, we know that lambda equal to 0 is the eigenvalue of A, if and only if determinant of A is 0. That means determinant of A is not 0, if and only if lambda equal to 0 is not eigenvalue of A. So statement 20 is equivalent to statement 7. Since statement 20 is equivalent to statement 7, that means statement 20 is equivalent to all other statements. So for these 20 equivalent statements, if one of them is true, they are all true. If one of them is false, they are all false.